Let's find the analytical, the theoretical magnetic field according to the law of Biotsavart of a straight current carrying conductor. This should look eerily familiar. And in the minute that it's going to take me to get the tablet set up, just take a minute and think about what we did for the electric field. Of a line of charge. All right. Let's give it a shot. Sources of magnetic field. I got temporarily lazy and I didn't want to type magnetic field. The field of a straight current carrying conductor. Suppose we have a conductor that is oriented along the x-axis, let's say. And let's further suppose that the direction of the current is in the positive x direction. We are interested. This, it's extends in both directions. So it's a very long, or we're very close to it so that it looks infinite. But here we are, a perpendicular distance r away from this conductor at point P. We will have to consider the magnetic field created by a infinitesimal current element passing so and so far away from point P. I'll show you what I mean. Suppose that we consider this bit of the current that is moving to the right. How much current are we talking about? I times dl. The point P experiences a magnetic field according to the law of biotsavart that we just wrote in the PowerPoint slide. Right? Right. I'm going to keep my symbols consistent. I'll use a lowercase I for current, dl for the length, and we need to know the distance between this blue line that we just drew. That's vector r. That's a little bit confusing. There's two different r's here. I'm going to go ahead and label this guy A for now, so that I don't get confused. R is the point-to-point distance between the infinitesimal current that we're considering and the point at which we would like to calculate the field. A is the perpendicular distance that the point P is away from the wire. And if we consider the y-axis as here, that point P is on the y-axis, then this distance is the x-coordinate. The x-coordinate of the infinitesimal current. All right, so we know the magnitude of the point-to-point separation distance. It's Pythagorean. Okay. Now, what about the direction? When we did this for the electric field, there was a whole thing. We had to convince ourselves that there was some symmetry to the situation and that all the different like perpendicular components were going to cancel each other out, and we were just going to have one sort of axial component away from the line of charge. But no matter which x coordinate we consider, the cross product involved from that differential current to the point P, no matter what we do, our right hand is going to say, okay, dl is a vector that points in the direction of the current. So I'm looking at the thing and I point my hand towards the right, towards the positive x-axis. And then I do the right-hand rule for cross products, and I cross dl into the position vector, r. That's for the left-hand side, that's the blue vector. My thumb points up, off the screen at my face. The same thing happens for the other differential element I just drew, and would happen for every other differential element along this conductor. Point our fingers in the direction of the current, cross them around so that they point in the direction of the position vector. My thumb points out of the page at my face. No matter which, all of the differential current. Now the magnitudes are different because they vary like r squared, but the directions of the differential field dB vector are all out of the page. Which means we don't have to do any component finding nonsense, not like we did for the electric field. Which is nice. We just need to integrate. We're integrating. I mean, we're basically integrating magnitudes because as far as the magnetic field is concerned, it's a single dimensional problem. Now, we do need to worry about the cross product because we need the magnitude of the cross product. So let me finish writing this. We need dl vector magnitude. We need to know r squared. The cross product of dl vector and r hat. Now, the magnitude of dl vector, I've written it already, but it's just dl. The magnitude of r hat is just 1 because it's a unit vector. The only other piece we need to write the magnitude of the cross product, because that's all we're doing, everything's in the same direction. So this is a magnitude question. Now that we've already established the direction, we just need the magnitude. So magnitude, sine of the angle between. But the angle, the sine of the angle between. Now, whether we're on the left-hand side for negative x or the right-hand side for positive x, the sine will be positive because we're either talking about an acute angle or an obtuse angle, the sine of which is positive regardless. We just need the equivalent triangle. We need sine is opposite over hypotenuse. Now, the opposite side is this one. It's the perpendicular distance A. The hypotenuse is what we called r. It's the square root. It's the Pythagorean. It's the hypotenuse. So sine theta Oh, wait, hold on. Before I get ahead of myself, let me finish writing. We got mu0 over 4 pi equals dB vector. But sine theta is A over that thing. So we had this to the 1/2, and then we squared it. But now we're going to do A over that thing again to the 1/2. That's sine theta. And then we still need to divide by x squared plus a squared itself. Okay. Thing to the 3/2. All right. So if we want the total magnetic field at point P, we need to integrate. Now, integrate from what to what? Well, we've got the conductor oriented from one side to the other along the x-axis. Let's say we're going from negative B to B. Or, I don't know, negative L over 2 to L over 2, or whatever. But if those are our bounds, because that's where all the current lives on the x-axis between negative B and B, as I just labeled it, what we're actually integrating, not dl, dx. Everything else is constant. We can pull it outside. mu0 I a 4 pi. The only thing left is this integral. Which just, I mean, it's sort of funny, right? Like when we were doing this for the electric field of a line of charge, we needed a trig substitution, and I'm looking at this thinking we're going to need another one. Suppose I skip that part and write what we know the answer to be. Because the trig substitution gave us some trouble last time. Don't need that. Maybe this one would have been okay as far as trig substitute. Like there was no, when we did that one, there was a whole thing with natural logs, and maybe this one would have been okay. Should we try it just to see? So what? We're going to let x equal a tangent. So that dx is a secant squared theta d theta. So that looks like a secant squared theta d theta all over. That's, hold on, the 3/2, it's throwing me off. So a squared tangent theta plus 1 all to the 3/2. Yeah. So we can get rid of the outer parentheses there. We end up with a squared half is just a, but we're going to cube that. So that's a cubed once we're done, which is nice because that gets us the 1 over a squared in the answer that I just wrote down. Tangent squared plus 1 is secant squared, right? One over a squared. 1 over secant. The integral of cosine. Well, that turned out quite a bit nicer than the one that I remember remembering. That's why. Because in order to be a trigonometric substitution, it has to be a possible triangle, which means the domain of theta can't be any larger than 180 degrees, which means sine of theta has no ambiguity. We're fully in the space where, like, we're accounting for all the ways that sine theta could be positive. When we talked, I think it was tangent or maybe cotangent or something like that, or cosecant, but there was some ambiguity the last time we did this, where there was another quadrant where it could be, so we had to consider multiple answers. You remember it was a thing. It came back, and we had to talk about it again. This one, I don't think we have any ambiguity for. I think sine theta is singly defined. Tangent theta is x over a. So we're talking a very similar triangle in our trigonometric substitution here. So sine theta is x over that thing. There it is, x over that thing. No plus or minus shenanigans necessary. Cool. I feel good about that. I feel good having done that. It would have felt, like the Wizard of Oz, pay no attention to the man behind the curtain. If we hadn't. Now, we have our result. That A and the other A gives us an A down here. And we're evaluating x from negative B to B. But we wanted this to be a long, straight current carrying conductor. B, for our purposes, might as well be infinite. Strictly speaking, this is the answer for a finite linear conductor. But if we are, in some sort of limiting case where we can argue that it is in fact infinite, or at least functionally infinite, then we are taking the limit as B goes to infinity. X over from negative infinity to infinity. All right, so what are the limits? If x is, this is going to be mu I 4 pi a, plug in positive infinity. Infinity over the square root of infinity squared, which sounds like 1. But that's a little bit hand wavy. A little bit, again, pay no attention to the man behind the curtain. Let's factor out x squared. In the denominator, and we can take the square root of that. So we have x times the square root of that. The x's we can cancel, and we have 1 over stuff. If x goes infinite, positive or negative infinite, well, now wait a minute. Aren't we going to get 0 then? Positive infinity is the easy one. We've got no problems. We cancel, we get a 1. X goes infinite, a over x goes to 0, the denominator becomes 1, and it's just 1. Oh, yeah. Infinity over the square root of infinity squared. Okay, 1. Minus, what do we get when we plug in negative infinity? And now here's the trick. When we factor x squared, out from the denominator and take that square root, technically we have lost the sign of X, what we have technically is the absolute value of X. So this actual X in the numerator, if we make that negative infinity, and we make this one the absolute value of infinity, when we cancel those, we're going to be left with a -1. As we might expect, the magnitude depends on the magnetic constant. It depends on how much current is carried in the conductor. And we know that the magnetic field lines are circles. Circles that are in a plane perpendicular to the conductor. Those circles have circumferences according to how far away from the conductor they are, 2 pi a. This is a very nice geometric result. And it has the 1/axial distance dependence that Bsources measured quantitatively. So we can show that the sort of formula that we're crediting to Bsources produces the correct strength dependence of a linear current. So we did the thing. Unfortunately, I adjusted some of the letters. The Young and Friedman textbook orients the thing differently, doesn't really change any of the math, and we end up with a completely analogous result. X, in this case, is the perpendicular distance to point P. So we want that X in the denominator to survive. The A's here cancel the same way that the infinities canceled in our derivation a second ago. And we end up with a perfectly identical result. And since the whole thing has rotational symmetry, instead of in the slides version, instead of calling it X, we might as well call it a radial distance away from the wire, or in the derivation we used with the notepad, letter A is already sort of axis irrelevant. You know, it's a perpendicular distance away. As labeled, it was the y-axis, but we could rotate the conductor a little bit, and now we're talking about a new y-axis, I guess. And we end up with the same result.